Dear students, after studying this module, you shall be able to know the differences between aliphatic and aromatic nucleophilic substitution in terms of rate of reaction, learn about the factors which affect the rates of aromatic nucleophilic substitution reactions, identify suitable substrates, leaving groups and incoming nucleophiles for SR-N1 reactions, Benzine reactions as well as SN1 type and SN2 type of reactions. Analyze factors which govern the suitability of reaction conditions for nucleophilic aromatic substitution reactions. Let us begin this topic with the introduction. For aromatic nucleophilic reactions, the basic mechanisms are SN-AR, Benzine and SN1 mechanism as well as the SR-N1 mechanism as described to you very clearly and in detail in the previous modules. The reactivity considerations are quite unimportant for aromatic nucleophilic reactions since in most cases there is only one potential leaving group in that molecule. Therefore, a lot of attention is largely focused on the reactivity of one molecule compared with the another and not on the comparison of the reactivity of different positions within the same molecule. Now, after having introduced to you various reaction mechanisms for aromatic nucleophilic substitution and what needs to be given attention in the same, let us discuss about factors which affect the rate of aromatic nucleophilic substitution. The common factors which influence the rate of all the three types of these mechanisms are substrate structure, leaving group and the solvent. Now let us discuss these topics in detail separately. First of all, we will discuss the effect of substrate structure. The SN-AR mechanisms, they follow an addition-elimination step, as you may recall from the previous modules as we have told you, where the first incoming nucleophile gets attached to the substrate and then elimination of leaving group takes place. In this type of reaction, aryl halides with suitably placed substituents, they react with strong nucleophiles to give substitution products. Interestingly students, such reactions proceed via an anionic intermediate often popularly called as Mesenheimer complexes. Since it is difficult for a nucleophile to attack an electron-rich center or a ring, when the aromatic ring contains deactivating or electron withdrawing groups, that means when these groups are present, they can help in removal or attraction of the charge or the negative charge which is placed on the ring towards itself. These reactions will definitely and obviously go faster because now the ring will be less in negative charge because of these electron withdrawing groups. So the nucleophile finds it easy to attack the ring. If the electron withdrawing groups are present at ortho and para positions to the leaving group, great accelerations in the rate of reactions has been observed. On the contrary students, if the substrate has electron donating substituents, then reactions they go slow. For common substituents is the order of increasing ability to activate aromatic rings for SN-AR substitutions. For example, you can see here the order, that is the nitride cation, the NO and the NO2 nitrate, the SO2Me, the NMe3 that means the trimethyl nitrogen, then the CF3, CN, CHO that is aldehyde, ketones, then is the carboxylic acid, then is the proton, then the sulfate SO3, the bromine, chlorine, iodine and the CO minus and the H. This is the order. As can be seen that the nitrogen containing substituents, they act as good ligands enhancing the rate of reactions manifold. Of note, the position of substituents, they also greatly influence the rate of reaction. For example, if the electron withdrawing nitro group is present at the meta position, then no delocalization of charge takes place and the occurrence or the rate of the reaction becomes slow, and the occurrence of the reaction becomes very difficult in this case. That is, when the nitro group is actually present in the meta position relative to the leaving group. As can be seen, if the nitro is present meta to the leaving group, then the reaction becomes very difficult. Now you can see this reaction happening at 0 degree as well as 25 degree. Now if you see here this table, then you can see all the groups which I have discussed above and the relative rates of reaction and where at this position, or whether the ortho, meta or para, where they are present, and how they enhance or decrease the rate of reaction in their presence. Now in case of SNAR mechanism, these comments are given. The Benzine mechanism of aromatic nucleophilic substitution, it involves elimination addition, whereby a distinct reaction intermediate, benzine, is produced. That is why it is considered as separate from SNAR reactions. In such reactions, products with substitution on the carbon directly bonded to the leaving group or to the carbon adjacent to it are formed in equal proportion. The benzine intermediate, students, has a triple bond in the benzene ring, which makes it a highly reactive species. When ortho and para substituents are present on the substrate, only one benzine intermediate can be formed. Now for this, you should clearly look at this figure. You can see that if the leaving group is X, then if it leaves, then if it is at the ortho position, only one possibility of the type of structure of benzene is obtained. However, if you consider the X present on the para position, then also there is only one possibility on how the structure of benzine intermediate will look like. Now you understand that when ortho and para substituents are present on the substrate, only one benzine intermediate can be formed. However, students, if we consider the case of meta substituents, when meta substituents are present, then there are two possible structures of benzines that may be formed based on which protons are more acidic and they are able to leave easily from the system. More acidic protons will be removed easily to form the benzine intermediate. Now you can see in this case where X is meta to the Z which is already present. Now students, see clearly, if the Z group makes the proton at the ortho position to Z more acidic, then this structure which has the triple bond in this center bond, that is the first structure, will be formed. If in case the proton in the para position to Z, that is the 180 degree to the Z, is more acidic, then the second structure or the second type of benzine intermediate will be formed. Now I hope it is very clear that in case of ortho and para substituents, no choice is left and only one type of benzine structure can be formed. However, in case of meta substituents, two type of benzine intermediate structures can be formed, and thus you can see that this is dependent on which proton is more acidic. Now students, this concept in itself is very important because of the fact that this can help you understand the mechanism of many reactions involving benzine as an intermediate. Also, it can help you in solving many problems where the product seems ununderstandable. But if you know the intermediate which is formed and the probable intermediate, then those problems can be solved very easily. The nature of substituents Z is decisive towards benzine intermediate formation in case when the substituent X is meta to the Z. An electron withdrawing group Z favors the removal of ortho hydrogen as explained by me earlier, whereas an electron releasing group favors the removal of para hydrogen. Now you might be asking the question to yourself that if the Z group is electron donating, it will donate both at ortho and para position. Here comes the effect of the proximity to the Z. Since the ortho position of the hydrogen is more proximal to the Z, then it will favor the removal of hydrogen which is far away from it, that is the para hydrogen. That will get removed and give you the second structure. Also, once the arine intermediate or the benzine intermediate is formed, there are two possible sites where the nucleophile may attack. That is on the two carbons which share that benzine. Again, the field effect of the substituent Z plays an important role in the decision, and an intermediate carbon ion which gets better stabilized by Z will be favored. For substituents with minus I effect or the minus inductive effect, the more stable carbon ion is the one in which the negative charge is closer to the substituent, because an electron withdrawing substituents which fall in the category of minus I effect substituents, they will pull over the negative charge of the carbon ion towards themselves, making it more stable, and thus that reactive intermediate or that carbon ion will be favored. Just as electrophilic aromatic substitutions were found more or less to follow the Hammett relationship as is discussed previously in the earlier modules, so do nucleophilic substitutions. But in this case, instead of sigma, we have a factor called sigma minus, which is applicable for electron withdrawing groups. Now students, after having discussed the effect of substrate structure, we will now discuss the second effect, which is the effect of leaving group on nucleophilic aromatic substitutions. The common leaving groups in aliphatic nucleophilic substitutions are halide, sulfate, sulfonate and the trialkyl nitrogen cations, etc. They are also common leaving groups in case of aromatic nucleophilic substitutions. But the groups nitro, OR, that is the ether groups, the OAR, that is the phenyl ethers, the SO2R and SR groups, that is the thioethers, which are not generally lost in aliphatic systems, are leaving groups when attached to aromatic rings. That is, they are leaving groups in case of aromatic nucleophilic substitutions. Surprisingly, NO2 is a particularly good leaving group. However, this depends greatly on the nature of the nucleophile, as illustrated by the fact that C6Cl5OCH3, that is pentachloromethoxybenzene, treated with NH2 minus gives mostly the pentachloroaniline. That is, one methoxy group is replaced in preference to 5 chlorine groups because it is a better leaving group, which is not seen in case of aliphatic substitutions but is common in case of aromatic nucleophilic substitutions. Stable anions are good leaving groups, which results in lowering of activation energy while reaction rate is increased. An approximate order of the leaving group ability is. Now you see here, we have given here the order, that is the approximate order of the leaving group capability of the groups in case of aromatic nucleophilic substitution. Now you have to see this very carefully, because by considering or by remembering this particular order, so many problems can be solved and you shall be able to know when two competing leaving groups are there, which one is a better leaving group and what product consequently will be formed. Now you see here that the best leaving group is the fluorine, then the nitro, then the tosyl, then the SOPH, then the chlorine, bromine and iodine, they are at the same position. then the nitride, then the Nr3+, that is the trialkyl nitrogen cation, then the OAr, that is the phenyl ether, then the OR, that is the aliphatic ethers, then thioethers, that is the Sr and NH2, and the phenyl ethers, they all are at the same position, that is at the end. Amongst the halogens, you must have noticed in this order, fluoro is generally a much better leaving group than the other halogens. Reason is its highest electronegativity, which have reactivities fairly close together. The usual order is, students, chlorine, bromine and then iodine, but this is always not the case. The leaving group order is quite different from that of the SN1 and SN2 mechanisms that have been taught to you. The most likely explanation is that the first step of SNAR mechanism is usually the rate determining step, that is the slowest step, and this step is promoted by groups with strong -I effects. This would explain why fluoro and nitro are such good leaving groups, because in the rate determining step or the slowest step, it is promoted by the -I groups. That is why fluorine, being such a small anion also, and also the nitro group, they are very good leaving groups in case of aromatic nucleophilic substitution, not observed in case of SN1 and SN2 substitution. Now students, fluorine or the fluoro group is the poorest leaving group of the halogens when the second step of the SNAR mechanism is the rate determining step, or when the benzine mechanism is operating. Now this is a very crucial and important note, because the SNAR and the benzine mechanisms, here the leaving group ability of fluorine is, or the fluoro group, is basically reversed because of the factors which actually govern the rate determining step or the slowest step. Here you can see in case of benzine, fluoro is the poorest leaving group. However, for the SNAR, fluoro was the best leaving group. So, moving ahead, the 4 halogens as well as SPH, NME3, that is the trimethyl nitrogen cation, and the OPO, OET whole twice, that is the phosphorus compound, have been shown to be leaving groups in case of SRN1 mechanism. That means these few groups are good leaving groups in case of SRN1 mechanism. The only important leaving group in case of SN1 mechanism is the N2+ cation. Now students, we have described to you why certain groups are good leaving groups in case of one mechanism and they become poor leaving groups in case of other mechanism, in case of nucleophilic aromatic substitutions. So taking care of these factors and remembering these few points, it is very easy to elucidate products in any given reaction to you. Now the next factor, students, is the effect of attacking nucleophile. It is not possible to construct an invariant nucleophilicity order, since different substrates and different conditions lead to different orders of nucleophilicity. However, an overall approximate order is discussed. That is, the NH2 comes first, then the triphenyl carbon anion, then the PHNH- which follows the arine mechanism, that is in case of arine mechanism this is applicable, ARS-, then the RO-, then the dialkyl NH, that is the secondary amine, then the ARO-, then the hydroxyl anion, then the aniline, then ammonia, then is the iodide ion, followed by bromide ion and chloride ion. Here you should see that iodide is the greatest as compared to bromide as compared to chloride. Earlier they were at the same position when we were discussing the earlier order, that is the leaving group order. which is greater than, coming back, iodide greater than bromide, then chloride, which is greater than water and then the aliphatic alcohols. In case of aliphatic nucleophilic substitution, nucleophilicity is generally dependent on base strength, and nucleophilicity increases as the attacking atoms move down a column in the periodic table. But there are some surprising exceptions to this. For example, hydroxyl anion, a stronger base than ArO-, that is the phenoxide ion, is a poorer nucleophile. In a series of similar nucleophiles, for example substituted anilines as described to you, nucleophilicity is correlated with base strength. Oddly enough, the cyanide ion is not a nucleophile for many aromatic systems, except for sulfonic acid salts in the von Richter and Rosenmund-von Braun reactions, which shall be taught to you in detail in the future modules, which are special cases of this reaction. Studies on the nature of nucleophile continue. Indeed, the second order rate constants for vicarious nucleophilic substitution reactions of some carbon ions were measured to define electrophilicity parameters for electron deficient heteroarenes. Now students, we have indeed in detail discussed the various factors which affect the nucleophilic substitution reactions in their varied mechanisms. Now we shall summarize this module. We have taught you in this module that the reactivity considerations are quite unimportant for aromatic nucleophilic reactions, because in most cases there is only one potential leaving group in that molecule. Therefore, attention is largely focused on the reactivity of one molecule compared to another and not on the comparison of the reactivity of different positions within the same molecule. We also told you that if electron withdrawing groups are present on ortho and para positions to the leaving groups, great accelerations are seen in the reaction rates in case of SN-AR reactions. However, the reverse is seen in case of electron donating groups. It is because in these nucleophilic substitutions, the intermediate possesses the excessive negative charge on the ring, and we need -I groups, that is the electron withdrawing groups, to decrease the negative charge on the ring. However, this is not fulfilled if the groups are electron donating in nature. For substituents with -I effect, the more stable carbon ion is the one in which the negative charge is more closer to the substituent, as in case of Benzine mechanism. As we told you, the common leaving groups in aliphatic nucleophilic substitution are halide, sulfate, sulfonate and Nr3+, that is the substituted amines, etc. They are also common leaving groups in case of aromatic nucleophilic substitutions. But the groups like nitro, OR, that is the ether, that is phenyl ethers, the SO2R, alkyl sulfates, and the thioethers, that is the SR group, which are generally not lost in aliphatic systems. They are very good leaving groups when attached to aromatic rings. Coming to fluoro and nitro groups, as we discussed, they are very good leaving groups in case of SN-AR reactions, because we told you of the intermediates involved in the rate determining steps or the slow steps. But they are poor leaving groups in case of Benzine mechanism, again due to intermediates which are involved or factors which are involved in the rate determining steps. Again, I would like to iterate, they are poor leaving groups in Benzine mechanism, but good leaving groups in case of SN-AR mechanism, because of the intermediates formed in the rate determining step. In case of aliphatic nucleophilic substitution, nucleophilicity is generally dependent on base strength, and nucleophilicity increases as the attacking atom moves down the column in the periodic table. However, There are many surprising exceptions to this fact, as chemistry is always. Now students, having discussed all the factors and mechanisms in detail in the previous and this module, I hope you will be able to solve the problems related to nucleophilic substitution aromatic reactions in a very nice and simple fashion. I hope you found this module very informative.